right, let's keep talking about Euler a little bit. I did email this theorem to you. And so Euler actually does have a theorem, which is awesome because the other one we're going to learn about does not. And so what you're going to do is you're going to look at the degree, and you're going to see if you have exactly 2 odds, no odds, or if a graph has more than 2 odd vertices, then that. Okay, so that's what we're going to look for. So we're going to look at the degree first. Okay, so like 2 roads going in and out, degree 2, 1, 2, 3, that's 4, 1, 2, 3, 1, what is it, 1, 2, 3, 4, 1, 2, 3, and there is not a point there. That's not a vertex. Okay, so let's look at our theorem. So before you start looking for an Euler, which again deals with edges, before you start looking at that, you look at his theorem because you could be wasting your time. So we have what? Exactly 2 odd vertices, okay? 4, even, but I have 2 odd. All right, so if I look at the theorem, it says if a graph has exactly 2 odd vertices, then it has at least 1 Euler path, but no circuit. Okay, so I know I'm only going to look for an Euler path. I'm not even going to try to find a circuit. And again, it's a good idea to usually start at the odds because kind of that whole getting in and out kind of thing to see if that works. So let's see if we start. Let's start at one of these odds. I'll start at D. So if I go D and I want a path, so I have to touch every edge. So it's not like you can just go around because you got to touch every edge. All right, so let me see what I can do here. And again, sometimes you might get it wrong at first. So we'll go D to B, and then we'll go from, so D to B. We'll go B to A. We'll get that edge knocked out. And then A to C. Okay, so those are all gone. And then I want to get this one while we're here, so I'm going to go back to B. And again, repeating vertices is fine. All right, now I'm going to go B to E. So B to E. And then I'm going to, let's see, we'll go up and hit C again and get that run. And we'll go C to D. And then D to E. Okay, all right, now notice we started at D. So we kind of went, what do we go? Dun, 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 dun. All right, so we started at D, we ended at E. So it's not a circuit, it didn't go full circle back, it's a path. But notice I only touch every edge once. So I went up, 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 back, dun, 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 dun. And I never went over the same road twice, basically. I went through cities multiple times, but he only cares about edges, 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 edges. Okay. All right, I'm going to pause it for a second. Why don't you look at the degrees of these, okay? And then this is a handout I emailed to you, but you're going to want that for the test. So look at this one, look at all the degrees, see what the theorem tells you, and then whatever it tells you, try to find it. If it's a path, if it's a circuit, whatever. All right, I'm going to pause for a second and let you do that. Okay, so hopefully you found the degree of everyone. And if you look, you have no odds. So it says if a graph has no odd vertices, all even, then it has at least 1 circuit. Now, notice if you have a circuit, you automatically have a path. So, because a circuit's kind of up above a path is beneath it. So if you have a circuit, you really have both on this one. Because if you have a circuit, you obviously did more than you should have, so you have a path as well. All right, let's see, where do I want to start? So again, I'm probably going to start, if they tell me where I have to start, I will start there. But since I get to choose, I might pick F and see where we go from there. All right, so if I start at F, I'm going to come over to A. And let's see. I need to save that to get back, right? So I'm going to go to B. And then I'm going to go down here to C. And then let's see, I'm going to go up to A. I'm going to go down to D. And I'm going to go back to C, which again is totally fine. I'm going to go down to E. And I'm going to go up to D. And I'm going to go back to F. Oopsie. Helps if you write the right letter. All right. So I started here, and I went over here, 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 and back. And again, this is how we typically write that. And it is a circuit because I started at F. I touched every edge exactly once. I no backtracking on roads. Okay, cities you can go through multiple times, but not the roads. And I looped back. So this is both because it's a circuit, right? But again, a path is kind of underneath a circuit. So if you get a circuit, you're going to be good to go. Okay, so that's Euler. All right, I'm going to regroup for a second. I have, let's see, this handout. So I want to look at this, and then we want to talk about Hamilton a little bit. Okay, so again, in real life, these represent things like if you're like, well, when am I ever going to use this? Well, you know, it goes with maps and things like that. So say I give you this map, and I want you to make a graph of it. Okay, so if you think about it, like each state is going to be a vertex. Okay, and you don't have to draw them, you know, exactly like it is, but I'm going to. Okay, so if you think about it, okay, Florida is connected to, not to Mississippi. Okay, so here's Alabama, this is Florida. So Florida is attached to that one. Florida is attached to Georgia. Florida is not attached to South Carolina, so it's just attached to two. Okay, Mississippi is attached to what? Alabama. And Mississippi is attached to Tennessee. Tennessee is attached to Mississippi, Alabama, Georgia, and North Carolina. North Carolina is attached to Tennessee, Georgia, and what, South Carolina? Okay, and then South Carolina is touching North Carolina. South Carolina touches Georgia. Does not touch Florida, and then these all connect. Okay, does that look about right? Let's see, Alabama does not touch North Carolina, so I think we got it right. So Mississippi did that to there to there. From here, I could either go there or there. From Georgia, I could go to North Carolina, Tennessee, Alabama, yeah, something like that. Okay, and then what we could do is, you know, do the graph theory on this. So we take our map and we convert it to this so we can do math on it. Okay. All right, let's look at another one with Euler Theorem. Let's look at this guy. Okay, so say this is our graph. Okay, and again, these are our vertices. All right, so the first thing you do with Euler is you start with degree. So 1, 2, 3, going in or out. 1, 2, 3, 4, 5. It's at 5. 1, 2, 3, 4, 5. Yeah. 1, 2, 3, and 1, 2, 3. Okay, and then you look at Euler's theorem. I have a bunch of odds. So if a graph has more than 2 odd vertices, there's no path or no circuit. So there's no reason to even do anything, right? So that's why you always want to start with the degree, because it's like, yeah, I mean, if it doesn't exist, why are you wasting your time? Okay, so Euler's theorem is going to be your best friend, okay? All right, let's talk about the other guy. Okay, so Euler cares about edges, and again, everyone exactly once, okay? So just exactly once. Hamilton, so sometimes we call these Hamiltonian ones. Well, if Euler cares about edges, there's only one thing Hamilton can care about, and that's the vertices, because that's all there are in graphs. There's edges and vertices. So Hamilton cares about vertices, okay? So Euler cares more kind of about the roads, like you only hit each road once. Hamilton cares more about the cities, like you want to hit each city once, and you don't want to backtrack through a city at all, okay? All right, so let's talk about a Hamilton path. Hamilton path is, you know, edges don't matter. You can go through the edges as many times as you want, okay? But a path, you're going to start and end, okay? So you're going to have a start and an end, and you're going to have to go through every vertex exactly once. Exactly once, okay? So no backtracking, okay? You can only go through everyone exactly once. But again, remember, a path starts and does not have to end at the same place, but you have to go through every single city. Edges don't matter, so you can skip edges. That's okay. You can skip edges, he doesn't care, but you have to go through every city exactly once, and you cannot backtrack and go through it twice. Okay, and then a Hamilton circuit is, you know, you have to start and return to the same vertex. And again, same as a path, you have to go through every vertex once, only once. So go through every vertex exactly once. But then you have to get back to where you started from, okay? All right, so say I give you, I don't know, we'll get this picture. Okay, right there, and say this is A, B, I don't know, C, D, E, doesn't really matter. Okay, so say I start at A. So if I go to A, to B, to E, to C, to D, and then back to A, that is an Euler circuit because I started at A, went to B, went to E, went to C, went to D, and went back to A. And notice I missed some roads. I didn't go down that one, didn't go down that one. That does not matter. But notice I did not backtrack either. So you can't go like A to B to E, back to A over here. You can't do that, okay? You cannot go through a city more than once. Say I give you something like this. Okay, and again, unfortunately, it has no theorem, so you just kind of have to try it. A, B, C, D, E. So if I start at A, and I go dun, 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 notice I have to go back through C. So if I start at A, I have to go through C, and I come down here, but then to get back up, I'm going to always have to go through C. If I start at C, I could do all this, but then, again, I'm going to have to go back through C again to get those up there. So C has none, okay? Or I mean, the shape has none, because the problem is that C1, you're just going to keep kind of hitting a wall with that one a little bit. All right, let's look at some other ones. So let's see what we got here. All right, so let's look at this one for, now we're focusing on Hamilton. So we're not Hamilton. We're not focusing on edges. We're focusing on vertices. All right, so let's see. If I go here, well, this one's not bad, right? Just go around the outside. And again, if you have a circuit, you automatically have a path. And again, you don't have to touch that. Nobody cares. Let's see here. And sometimes you don't even know where to start, so that's the problem too. Like it might not work if you start here, but it might work if you start here. But this one, again, is the same, really, actually, because you just have to hit all the cities. Okay, let's look at this one. All right. Yeah, same thing. I can just go here, hit that city, and again, get back. All right, let's look this one. Now, again, bridges are always kind of a good place to start. So with Hamilton, this one looks problematic. So you usually want to start at like a bridge. So say I start at E, go here, go here, go here, go here. That's a problem because see how I have to go back to a city I've already been to. And if I start somewhere else, usually, again, bridges are your best choice. But if I start, like, say I start at A, which is not a bridge, but say I start at A, and then I go here and here. But see, then I have to come out here to get that guy. And then, again, I'm stuck because, you know, you can't backtrack to a city you've already been to. So this one would have none. Yeah, that's about that one. There is one theorem with Hamilton, just one. It's not a great one, but it's called a complete graph. If you have a complete graph, which again is rare, that means every city can get to everything. So if I'm at A, I could get to B, C, D, E, F, all from A. Like everything is connected. So that's what a complete graph is. So if it's all connected, there is one theorem with Hamilton, which says there's n-1 factorial unique circuits. Unique, meaning they're actually different. They're not just rotations of the same. So n is your number of vertices. So if I count them, right, I have 1, 2, 3, 4, 5, 6 vertices. So 6 minus 1 factorial, I have 5